Hey YouTube, I bought a couple of these so-called driverless LEDs to see if they could be used for lighting high-speed video. They can be directly connected to mains power, and have an internal rectifier that helps drive the LEDs. However, LEDs all have a minimum forward voltage. This is the voltage below which no current flows, and therefore no light is produced. You can see as I gradually increase the voltage applied to these LEDs, nothing happens until we hit that certain minimum voltage. Above this voltage, current can flow through the LEDs and light is produced. Internally, a full bridge rectifier changes the mains power into a series of DC pulses. When the voltage of these pulses is below the forward voltage of the LED array, no current can flow. This means that periodically the LEDs turn off completely, resulting in the strobing that you can see in slow motion footage. In order to eliminate this strobing, I built a filtered DC power supply. This power supply uses some capacitors, a rectifier, and a large inductor to supply a smooth DC source to these LEDs, eliminating the ripple in its supply and therefore eliminating the pulsing of the light output. My first attempt used only a rectifier and a capacitor, which worked fairly well but still left about a 20-volt ripple in the power which was arriving at the LEDs. This made the LEDs stay on constantly, but their light output was modulated by this 20-volt ripple. By adding a large inductor and another set of capacitors, the output was smooth to the point where the ripple was less than 1 volt, resulting in very even lighting from these LEDs. An easy mental model is to think of the capacitors like balloons or springs. Charge is pushed into them and held there under pressure. The inductor can be thought of like a flywheel for current. It resists changes in the amount of current that is flowing through it. When power is first applied, the first capacitor immediately begins to charge. Current also begins to flow through the inductor, however somewhat slower, charging the second capacitor. After the voltage from the rectifier peaks and begins to drop, it can no longer charge both of the capacitors. However, the flywheel effect of the inductor uses charge from the first capacitor to charge the second. This makes the voltage on the second capacitor and across the LEDs much more stable. There are a couple problems with supplying power this way. The first is that these LEDs are made for 120 volts RMS. RMS, which means root mean squared, can be thought of as if it's the effective DC voltage you're applying when you're using AC. If your RMS AC meter reads 120 volts, it's the equivalent power you would get as if you were using 120 volts DC. When using my filtering DC supply, I only have to give it 80 volts RMS in order to get the 110 volts DC that these LEDs need to run. Had I plugged my filtering DC supply directly into the line, they'd be getting 170 volts, which significantly shortens the lifespan of the LED. The other problem with my power supply is that the capacitors hold a significant amount of charge even after the power supply has been turned off. To mitigate this problem, I've put high-value resistors across all of the capacitors in order to dissipate the charge once power has been removed. Although this isn't a permanent solution, it is significantly cheaper than any of the commercially available high-speed video LEDs, and it allowed me to learn a little bit about analog power supplies and filters. I hope you found this video interesting, and if you'd like to see more like this, check out my channel. Thanks for watching.